Hope you guys are doing well. Had your cup of teas, right, Isaac? Good man. And so all we want to do here is that, well,
I totally missed that. What?
This is we're in chapter 8, just making sure you're still awake. Okay.
So
Okay, here we go. So let's get started. So we are in chapter 8. We're going to look at the complete response of two storage element circuits here. So when we're looking at this thing, what you're going to see here is that we're going to see the following thing. We could have three types of circuits. So if I talk about a two storage, so a two storage circuits are either RLC, RLL, or RCC. And what we're going to find here is that what we're going to see here is that these are second order differential equations that have a solution form of x of t. Then there's going to be the natural response, and then there's going to be the forced response. Now, it turns out that the natural response is a lot more challenging now. So this guy here is more challenging. And because it's more challenging, to try to make the circuits more manageable, that is with time, what I'm going to do here is that I'm only going to consider constant sources. No time-dependent sources. And I got to be really careful here, because if I was to consider a time-dependent source, these problems take a long, long time. A long, long time. And so as a consequence, you're always going to see that the force response, B, is going to be a constant. So no time-dependent force. So we always will know what the force response is, because as soon as we derive the equation, our force response, we should know it like automatically. And you'll see that we'll go through the process. So what you're going to find here is a lot of our time now is going to be now. So most of our time will be getting the natural response. That's where we're going to spend. And what's really amazing about circuits here, second order circuits, is that they have the exact same equation as a harmonic oscillator system. So surprisingly, the differential equations for two storage element circuits and harmonic oscillators with damping are the same. And that is crazy. That is really surprising. So what we're going to see here is that the natural response can only take on 3 flavors. One, it could be overdamped. Two, it could be critically damped. And you'll see that critically damp is actually, in a lab situation, it's actually quite hard to actually see this. You have to be just at the right setting. It's like you're literally at a knife edge when you're looking at critically damped. And then the third one here, which will be underdamped. So what you'll see here is in the lab that we're going to do, we're only going to be looking at overdamped and underdamped. Like I said, critically damp is a very fine line to actually walk in order to do that. So what we want to do here is that I want to look at the problem-solving strategies. Okay, and they're very similar to the problem-solving strategies that we did with first-order circuits. And you're going to see that there's 5 steps. So the problem-solving strategies that you're going to see here is that our step 1 is going to be to determine the second-order equation. I'm going to put a lot of stress on you. You got to get step 1 right. I mean, you can't mess up on step 1. Because as far as I'm concerned, you get the wrong differential equation, you're solving a different circuit. So, I mean, should I give you a pat on your back and say, like, good try? No, hell no. You're solving a different circuit than what's being done. You gotta get that second order equation right. And I'm gonna spend a lot of time deriving that. And then you're gonna see that we're gonna go to step 2. We're gonna get the complete response. From the complete response, we go get the initial condition. There's a minimum of 3, sometimes 4. And then we got to derive our natural response constants, A1 and A2, put it into solution form, and of course, we solve the circuit problem. So the 2 things you want to be most afraid of. Step 1, step 3. And what you're going to find here is that step 1 and step 3 are very, very closely related to each other. So here's what we want to do here. So I'm going to start with step 1. Okay. We're going to be deriving the second order equation. And you're going to see that you're going to have to be the master of what? KVL and KCL. Okay, this step right here is essentially the time-dependent step that you saw in at the end of chapter 7. Well, this is that on steroids. You gotta get really, really good. Now, what I'm going to do here is that I'm going to be very, very formal about this. Okay, very, very formal. But in the end, what we're going to do here is that we essentially have to write down 2 equations and 2 unknowns. That's what we got to do at the end. And in the beginning, like I said, I'm going to be very, very formal. So what you're going to see here is that we're going to use 2 methods. we'll use two methods to derive these equations. So one method is going to be called the direct method. And the second one, I'm going to call it Kramer's method. Kramer's method is an operational method. The direct method, you deal directly with the differential equations itself, with derivatives. Word of advice, I'm only doing the direct method to get to the operator method. This is your method of choice. There are certain circuits that if you try to do it with the direct method, I'm just going to say, good luck to you. The operator method, Kramer's method, always works beautifully. Even in the situations that the direct method don't work. Yeah, and what you're going to find here is that a lot of schools only deal with the direct method, which is a real handicap, especially if you get an RLL or an RCC circuit. Man, that direct method, I mean, it's just a piece of shit. You don't want to deal with that. So what we're going to do here is that just to give you an overview, okay? So what we're going to do here is that I'm going to give you an overview of what these methods contain. So the first thing that we should look at is that you're going to find here is that one uses KVL and KCL. And usually it's really a KVL and a KCL. Sometimes it's two KCLs. Sometimes it's two KVLs. So one uses KVL and KCL. And what you're going to do here is that you're going to generate two first order equations. That contain VC, IC, IL, VL. So you're going to get four variables. Okay? You're going to get four variables. So the idea here is to do something like this here. So if I have KCL, then that means I have to do what? You're going to find that you're going to have to connect either, let's say, IC and IL, and then you're going to have KVL, where you're going to have to connect VL, VC. Okay? And what you're going to find here is that once you do this, then what you're going to find here is that you're going to have two first order equations with four variables. So now we have two first order equations with four variables. And so then the very next thing that we're going to do here is that we need to then rewrite these things. Here, apparently I have some stuff from office hours that I thought I got rid of. And then what we're going to do here is that then we can use the capacitor equation to convert IC into a VC equation, and the inductor equation, which is VL equal to L di dt. We can then use these to get two equations with two unknowns. So ultimately, we're always trying to take two equations with four unknowns and then convert them into two equations and two unknowns. So then here comes the second piece here. How to generate a second order equation depends on the approach. One, we could use the direct method, which uses derivatives, or two, we could use Kramer's method, which uses operators. And so these operators, they all use the same symbol as a Laplace. I'll use S, but that's a fairly standard thing here. And what in the end, what you're going to get here is that both methods have to give you something like this. You have to get a differential equation that's going to look something like this. And then this guy here is going to be equal to a constant. You should never, ever have an equation with minus signs. There should always be constant. Now, the constant on the right could be negative, but not this guy right here. Okay, so that's the overall view, is that we're going to generate two equations, four unknowns, and then we're going to use the capacitor and the inductor equation to convert them into two equations and two unknowns. And then how we generate the second one is the second order equation will do that. So what I'm going to do here is that this is right out of my lecture notes. So I'm just going to copy and highlight what I have written in there so that I could show you what it is that I'm going to do. So I'm going to stick this in here and then I'll go over it, but it's really the application process that becomes important. It's me. So method one is called the direct substitute method here. Now, what we're going to do here is that it says step one here says the following thing. It says 1.1, define the variables x1 and x2. Well, this may seem silly. It's not. And the reason why it's not silly is because when you're lost, this process may really help you. So what I'm going to do here is that when I define my variables x1 and x2, if I'm solving for VC, then I always choose the second variable for what I'm going to solve for. So if I want to write a differential equations for the voltage of the cap, then x2 should be VC. If I want to solve for the current of the inductor, then I call x2 IL. So it's always the second variable that I'm after here. And what you're going to see here is that you're going to see that later on, this becomes useful on how I write that down. Let's go to step 1.2. Now what you're going to do here is that I need to derive two first-order equations using Kirchhoff's laws. So I'm going to apply KCL and KVL, where KCL is going to relate to two currents, the current of the cap and the current of the inductor. And then I'm going to use KVL to relate the voltage of the cap and the voltage of the inductor. Then a very important step here is that I need to rewrite all resistor current and voltages in terms of these four variables: VC, IL, VL, and IC. Okay. So now I have two equations, right? I now have right here is that I have two equations for unknowns. So what do I got to do? I got to convert them into two equations and two unknowns. So then I'm going to rewrite VL and IC in terms of the capacitor and inductor equations. And then here's another key step right here. I need to identify equations 1 and 2. Now, how do I define equations 1 and 2? Well, it's connected to step 1.1. The equation that we're looking for is that the equation that contains the derivative of variable x2 is what we're going to be looking for here. So I'm going to identify that as equation 2. So if I'm solving for the voltage of the cap, then the equation that has the derivative of the voltage of the capacitor is my equation 2. If I'm solving for the inductor current, then the equation that has the derivative of the inductor equation is equation 2. So then I come to step 1.4. And what it says here is that now I'm going to substitute equation 2 into equation 1. And in that process, I'm going to derive my second order equation. And then what we want to do here is that now that I got a second order differential equation, what I want to do now is that I want to do a simple check. Does the steady state value make sense here? And since we're only dealing with constant sources, right? We're only dealing with constant sources. That means that the steady state of whatever I'm looking at must be a constant. So if I substitute this, so I'm going to call that steady state equal to B. So if I substitute in there, the first two terms on the left have to be 0. So then that immediately tells me what the steady state value is, that it should be related to that K divided by my A naught cofactors. So that's a very simple way of looking at that. Okay, so note, step 1 has freaking 5 steps. So we got to make sure that we actually go in and practice this. So what I'm going to do, I'm going to give you 4 examples of deriving the differential equation. And whenever I get a chance in future examples, I'm going to keep deriving the differential equation. You got to get this right. Okay, so remember, the only reason why I'm doing method 1, the direct substitution method, is because most of you guys have not used operator methods other than Laplace. And some of you are not very comfortable with Laplace, and some of you are comfortable. So this has a lot of similarities, but not the same. So here I go. I'm going to do an example circuit. And what am I going to do? I'm going to follow this process here. So here's my circuit here. So my circuit looks like this. I have a current source. I have a 1 ohm resistor. I have an inductor. And then I have a capacitor. So I'm going to call this I source. All I know is that it's a constant source, but I'm going to assume that it's time dependent, and you'll see in a reason why that is. And when you look at this, this guy is a 2 Henry, and this guy is a 1/2 farad. So when you look at this circuit, I mean, when I look at the current of how's this thing going to flow here? Well, clearly this guy has to be the inductor current, which then means that the voltage of the cap must look like that. So here I go. Let's go do it. So what I want to do here is that I want to define, I want to calculate, I want to derive the second order equation for the inductor current. That's what I want to do. So here I go. Step 1.1. What do? I define x1 and x2. What am I solving for? I'm solving for x2. In other words, the inductor current. So therefore, x1 must be VC. So right away, right, you can't get more simple than this. Why do we do this? To help us later on. Okay. So far, so good. So now we're going to go to step 1.2. And here we need to derive 2 first order equations. So let's go do that. So now what I got to do here is remember. So the first one, I got to apply KCL to relate IC and IL. So let's go look at the circuit here. So if I look at the circuit, you can clearly see that when I look at this, of course, I have a node right here. You could see that the current source is going to come in. Part of the current's going through the 1 ohm, and part of it's going through the inductor and the cap. The fact that the cap and the inductor are in series, they have the same current. Okay, so this tells us here is that we have the inductor and cap are in series. That implies that the inductor current must be the same as the capacitor current. So now I do the exact same thing with, okay, so this is a 3-step process here. So now what am I going to do? I'm going to apply KVL to relate what? VC and VL. So the first thing that I look at the circuit here is that note that the voltage across the 1 ohm resistor is in parallel to both the inductor and the capacitor. So what you're seeing here is that the 1 ohm is in parallel to both inductor and the capacitor. So this tells me here is that the voltage of the 1 ohm resistor must be the voltage of the inductor plus the voltage of the cap. So when you're looking at this, note that this is 2 equations and 2 unknowns. Sorry, not what I meant to say. So right here, you could see that these are 2 equations and 3 unknowns. But we want 2 equations and 4 unknowns. And you could see that the problem is the 1 ohm resistor. So my job now is to relate the voltage of the 1 ohm resistor to one of the 4 variables, which then brings us here. So now what we got to do here is that we need to rewrite the voltage of the 1 ohm resistor into a function of either, right, VC, IC, IL, VL. So what do I know about this guy here? Well, for starters here, note that when I look at the voltage of the 1 ohm resistor, I could either, so note, I either have the voltage of this guy, or I could think about this as the, or the current of the 1 ohm resistor. So I really have 2 choices here. Am I going to deal with the voltage, or am I going to deal with the current? Now, it turns out that, you have a way of dealing with this a couple of ways here. And what I'm going to do here is that when I look at this, what I'm going to say here is that I can rewrite the current of the inductor and the source into I1. So if I look at that, so from red node and circuit, you could see here is that what am I getting? I'm getting the source current. This is the 1 ohm current. And of course, I have the inductor current right there. So you could see that if I apply, so from the red node in the circuit, apply KCL. So then I get that I source is then going to be I1 ohm plus IL, which then says that I can rewrite the 1 ohm resistor as I source minus IL. So then that means here I can rewrite that term now. Okay, so if I rewrite that term, what I'm seeing here is that I now have 2 equations and 4 unknowns. So what I'm going to do now, so if I sub this in, we finally get IL equal to IC. And now look at this. This is going to be what? 1 times IS IL, which I'm going to write as IS IL, is then going to be VL plus VC. So now I have my 2 equations and 4 unknowns. Okay. Now we have 2 equations, 4 unknowns. And of course, my unknowns are VC, IC, IL, VL. And that's where we want to go. So here we go. So now I go to step 1.3. So what I'm going to do here is that now we want to rewrite VL and IC in terms of capacitor slash inductor equations. So let's go do that. So now if I do that, look at the first equation. Here's what I have. So if I look at the first equation, I have that IC, of course, IC should be what? remember, it has a half a farad. So I'm going to rewrite this guy. So this guy, so the way I rewrite this here is that I'm going to use what? This has to be C dV dt. So in this case, it's going to be 1/2 dV dt, and that's going to be IL. Then I go to the second equation. What you see with the second equation, what I'm going to do here is that I'm going to do what? See that I source? I'm going to isolate that term, and I'm going to bring IL to the other side. So then my second equation tells me that it looks like this. I have IL plus VC plus VL, and then I'm going to replace VL by L di dt. And look at the inductor. The inductor has a value of what? Has a value of 2. So then I'm going to write this as IL VC plus 2 di dt. And this is going to equal to I source. So now look what you see here. We started off with 2 equations and 4 unknowns. Now, what you're seeing here is that here and here, I now have 2 equations and 2 unknowns. My unknowns, of course, are IL and VC. So now what we got to do here is that the next thing that we do here is that we need to identify which is equation 1 and equation 2. And since we are solving for IL, the term di dt is equation 2. So when I come up here and I look here, you could see that this equation over here on the right, this guy here, has the derivative. So this now is equation 2 because it has the inductor derivative here. This guy here is therefore equation 1. Now note, all hell breaks loose if equation 1 and equation 2 both contain the derivative of the inductor current like this. So what you find here is that here's where the direct method really sucks. I mean, it's pathetic. That's why we need the operator method. Okay, because this technique does not allow you to do that. So now that I've identified 1 and 2, I'm finally going to go to step 1.4. And what we're going to do now is that we're going to use substitution to determine the second order equation. Okay, so here's why it's worth labeling them 1 and 2 here. So what we're going to do here is that there's a 2-step process here. Okay, so there's a 2-step process. So the first step that we're going to do here is that you need to solve for VC in equation 2. Okay, so here's equation 2. So if you look at equation 2, what you're seeing here is that equation 2 reads like this, right? I got to solve for VC. So look what I got to do. I got to take everything to the other side. So I'm going to get VC is then going to be equal to I source minus IL minus 2 di dt. And you could see that I'm rewriting VC in terms of the inductor currents. So if you were going to look at this thing, this process is the start of eliminating VC from the equations. So now that I have this, I'm now going to go and substitute this into the next step here. So now what I'm going to do next here is that now sub equation 2 into equation 1. So let's go get equation 1. So when you look at equation 1, you could see what it looks like. So now let's go look at 1. So here's equation 1. And when I look at this thing, it's going to be equal to what? It's IL equal to 1/2 dV dt. So now I'm going to substitute equation 2 into here. So this is going to be 1/2 d dt. And then I got to put that whole thing in there. So if I take the derivative of this thing, I'm going to say, I'm going to assume that the source is not a constant. So I'm going to get 1/2 di dt. And then I'm going to get 1/2 of dIL dt. And then I get a minus 2 divided by 2 is going to give me 1. So I'm going to get di dt. And so now what I'm going to do here is the last step. I'm going to put it into proper form. Now put into proper form where di dt term has no cofactor. So if I bring over the two derivative terms to the left, what you're going to see here is that I'm going to get di dt squared. Now I got to bring over the first derivative, di dt. And then on the left here, I have IL, and then this guy's going to be 1/2 dis dt. And that's my differential equation right there. Now let's go to the final step. So the final step is that what I want to do here is that I want to do a simple check. Okay, let's do a simple check. On second order equation. And what we're seeing here is that because we have since we will only look at constant sources, IL at infinity must be equal to a constant. And I'm going to call that constant B. You could call it anything you want. This guy is the forcing constant. So I know that the inductor must be a constant. So when I look at this, what I'm going to do here is that I'm going to sub IL at infinity equal to B into second order equation. And what do I get here? Well, I get that I get the second derivative of a constant plus 1/2 the first derivative of a constant. And then I'm going to get b, and this is going to be 1/2 I source like this. So right away, what I'm seeing here is that, of course, this is 0. Of course, this is 0. Now, if I have a constant source, if we have a constant source, that implies then that the derivative of this guy must be 0. So if this is the case here, this implies here is that b must be equal to 0. It must be equal to 0. So now what I want to do here is that I want to check this with the circuit. So I'm going to go upstairs. I'm going to grab that circuit. Here's my circuit right here. So if I look at my circuit, here's what I'm seeing. It looks like this here. So I'm going to take this all out. And what we're seeing here is that when I look at this circuit, what I'm seeing here is that as this thing goes to its final steady state, what should I see here? Well, I have a current source. I have a resistor. The inductor should go to a short, and the cap should go to an open. So that means that this guy is going to be VC of infinity. And in this case, it should be the voltage of the 1 ohm resistor here at infinity. And then if I look at the current of the inductor, we could see that the current of the inductor, since that's going to be an open, is 0. So check that out. We see, so what I'm going to do now is that if I compare both of these guys here, right? These agree. And as a consequence, we then say that as a simple check, it looks like our differential equation is good. So now let's go to our first example. Let me make sure I'm ready here. So the first example looks something like this here. So it says, describe the behavior of the cap's voltage, and then determine the second order equation for VC using the direct method. And then, of course, check to see if the equation agrees with what you expected here. Well, what do I see here? This is what I expect here. So we expect that at t equal to infinity, we expect that Vs, that I'm going to have a short here, right? So this is my 2 ohm, this is my 100 ohm, and then my cap should be the voltage of the, should look something like this here. So in other words, my inductor current should be the current of the 2 ohm resistor, and my cap voltage at infinity should be the voltage of the 100 ohm resistor at infinity. So if I look at that thing, if I use voltage divider rule, we could see here that the voltage divider rule should be what? That this guy should equal what? 100, 100.2 times Vs. So that's the value that we expect to get right there. Now, I'm assuming here that when they're talking about 0 plus, well, I'm assuming that the source does only turns on at t equal to 0. So I assume that what I really have is I have a function like this, which is either 0 for t equal to 0 minus, and then this guy should be Vs at t equal to 0 plus. So what this tells us here is that the initial condition of IL at 0 minus should be 0, and at VC at 0 minus it should be 0, because we're not given any information as to whether this thing is charged up or not. So you have to assume that nothing's there. So then, of course, this tells us here that IL at 0 plus is 0, and VC of 0 plus is also 0. So let's go look at the process now. So now what we want to do here is that we want to derive the second order equation for VC of t. Let's go do that. So we'll try to move a little bit faster here since we've gone through the process already. And so that's what I want to go do here. So I'm going to carry this circuit around with me so that we could keep looking at this guy. So the first thing that I'm going to do here is that I now know the process of what I got to do. So I'm going to carry this guy around with me. Now keep it out here so that we always have it in sight. So here I go. Step 1.1, I'm going to define x1, x2. We're solving for VC. So clearly, I'm going to set x1 equal to IL, x2 equal to VC. Now, the next step, I have to calculate two first order equations. So I need to, I need to derive two first order equations. So here I go. So I'm going to look at my circuit here. Look at my circuit. That means I'm going to use KCL. And what am I going to do? I have to relate IL and IC. And then I need to use KVL to relate VL and VC. So let's start with the first one. So if I look at the first one, what do I know here? I know that this is the current IL right here. And I see that this current here is IC. So if I look at this red node again, look at this node right here. You could see here is that I could define a new current for the 100 that goes right there. So applying KCL at that red node here, let's call that node, God, I hate to say node A. How about if I call this node X? So what I'm going to do here is that I'm going to apply KCL at node X. So I could see right away that I got IL has to be I100 plus IC. Okay. So you know what? I'm going to start to do something a little bit different here. And I'm going to move this over here just for organization, just to tell you what I'm going to do. So look what I'm going to do here now. I'm going to start to streamline the process here. So look what I did. I applied KCL at that node. focus on this guy now. What do I know? Look at the 100. That's a resistor. So when I look at the 100 ohm resistor, note that the 100 ohm resistor is in parallel to VC. So what I'm going to do now is that note, I have to rewrite all the resistors in terms of the four variables, VC, IC, IL, BL. Since it's in parallel to this, then I see that the voltage of the 100 is the same as VC. So then I'm going to use Ohm's law. And if I use Ohm's law, then I see here that the 100 has to be the voltage of the 100 divided by 100, which is the same as VC divided by 100. So if I write this out, then I'm going to continue to move in this direction. So then this tells me here that this is IL, and look what I'm going to do. I'm going to replace I100 in terms of what? VC 100 plus IC. So look what I have. I have one equation that has three unknowns. Okay, now let's go apply the next one here. So I'm going to apply KVL. And what I got to do here is that I have to relate VL and VC. So let's go do this here. So the only way I can do this here is note what I got to do. I have to apply a KVL loop around the outside. That's the only way I can connect them. So what you're going to see here is that I'm going to take a loop that looks like this here. I'm going to do a KVL loop all the way around the outside loop. And because I know the inductor current direction, that means that the 2 ohm resistor has a polarity like this here. So I'm going to do here is that I'm going to apply KVL around outside loop. So here I go. Starting with the voltage source, look what I'm going to do here. I'm going to go minus Vs, then I'm at the 2 ohm. So I got plus 2 ohms. Then I got the voltage of the inductor. Then I come around and I got the voltage of the cap, and that has to equal to 0. Look at this guy now. Look at this guy. That's a resistor. I have to convert the resistor values into either IL, VL, VC, IC. So what am I going to do? I got to convert that. So look that the 2 ohm resistor is in series with the inductor. So that means they must have the same current. So then I'm going to say V2 ohm is then going to be 2 times IL. Okay, so look what I'm going to do. I'm going to take the source to the other side now. So then I'm going to rewrite the 2 ohm resistor in terms of 2IL plus VL plus VC is going to equal V source. Look what I have. Look what I have. What you're seeing here is that I have 2 equations, 4 unknowns. Okay. Again, what are my unknowns? VC, VL, IL, IC. So now I got to convert them into 2 equations and 2 unknowns. So now I'm at step 1.3. And on step 1.3, what I'm seeing here is that I got to come in and I have to then go in and I have to rewrite. So now I'm going to rewrite IC, VL with capacitor, inductor equations and define equation 2. So if I look at the first one that we did, so if I look at my KCL equation, you could see here is that this guy's going to be IL is going to be VC 100 plus IC. So let's keep bringing that circuit down with us. Let me find my mouse. So if I now paste this guy right here, I could keep seeing here that I have what? That I see that IC, look what I have. I have a 10 microfarad. You know, that's painful to write down. I strongly recommend that when you start getting to real values, do not put in numbers unless the numbers are simple. So I now see that IC is then going to be C dV dt, where C, of course, is 10 microfarads. So then this means here that I'm going to get what? VC 100, and then this guy's going to give me V dV dt, and now this guy's equal to IL. That's my first one. Now go look at KVL. KVL, if you look at the equation, reads 2IL plus VL plus VC. Now look at VL. It should be L di dt. And if I write that in there, I'm going to get 2IL plus L di dt plus VC, and this guy must be equal to V source. So now I've converted these guys. And so the question is, what is equation 2? Which one is equation 2? It's the one with dV dt like this. And right away, you could see here that this must be equation 2. Therefore, that is equation 1. So now that I've identified it, I'm now going to go in and I'm going to now get my differential equation here. So if I look to get my differential equation, what I'm going to do now is that I got to go in and I'm going to do step 4. And what I'm going to do here is that I'm going to substitute sub equation 2 into equation 1. So remember, what this does here is that I'm essentially eliminating the inductor current from the equations. So it's a two-step process, right? So the first thing that I'm going to do here is that I'm going to solve for IL in equation 2. And when you look at that, you can already see that we have it in that form. So we see that I have equation 2. And what I'm seeing here is that I already have IL in terms of VC 100 plus C dV dt. So I now have it in the right form. So now the thing that I'm going to do here is that I'm now going to sub equation 2 into equation 1. So if I look at equation 1, what do I see here? Well, you could see that my equation reads like this here. It reads that this is 2IL plus L di dt plus VC. And now I got to substitute this in here. So if I substitute this in there, I'm going to get 2 times the quantity VC 100 plus C dv dt, and then I have L. Now I got to take the derivative of that term. If I take the derivative of that term, what does it look like? You know, I'm going to run out of space. So I'm going to move this down. Okay, I'm going to run out of space. So now I got to take the derivative of this guy, and this guy should be 100 dv dt plus c dv squared dt squared plus vc, and this whole thing has to be equal to vs. So now my job here is to go in and isolate the terms here. So I got to go isolate this. So now I'm going to rewrite this thing to get into proper form. So I'm going to come in, and you could see that I have my first term right here. And then I have like terms. And then I have these like terms. So I got to combine them. Okay. So here's my first term. So my first term is the red term. So I'm going to get what? I'm going to get LC. And this guy's my red term right here. Now I'm going to get all the green terms. So I'm going to see that I'm going to factor out 2C plus L 100. And this guy's going to give me VC dt. And that gives me my green terms. And then I got to go get my single terms. So you could see I'm going to get what? 2 over 100. And then I get 1. And that gives me VC. And all of this has to equal V source. Proper form means that I have to isolate this guy, right? Proper form implies isolate. And why do we do that? Because that's what we're going to do. And then when we get to steps 2, that becomes very powerful. So then that means I got to divide. So this implies I divide everything by LC. So if I do that, I then going to get this guy. Now everything gets divided by LC. So this will be 2C plus L 100 LC. Then I get the other constant here, which will be 2 100 plus 1 divided by LC. Actually, I think I want this in brackets. And this will be VC. And then I got to divide the source by LC. And it looks like that. This is my differential equation now. Okay, that's what it is here. So if I punch in the numbers, okay, so now what I really got to do is I got to go check to see if this works here. So what I'm going to do here is by sub in L equal to 10 to the negative 3 henries and C, which will be 10 times 10 to the negative 6 farads, what you're going to find here is that you get numbers for these equations. You're going to get dv dt squared plus 3000 plus 1.02 times 10 to the 8 VC, and this will be equal 10 to the 8 VS. So now I have my numbers here. So now let's go do the final step. And we want to check equation and determine force response B. So once again, VC at infinity should be a constant since we're only dealing with constant sources here. So what does the equation tell us here? Well, right away, what we're seeing here is that I'm going to get which immediately tells us that, of course, this is 0 and this is 0. So then that means that this guy's going to be 1.02 times 10 to the 8 times b, and that has to equal 10 to the 8 v source. So right away, what you're seeing here is that I can cancel out the 10 to the 8s. So therefore, this tells me here is that b must be v source divided by 1.02. Okay, that's what my equation is telling me. But note, we looked at this guy already. Okay, and what we did here is that if I go to the circuit, let me go bring that circuit down so we could see it again, just to remind you what we did. And what we're seeing here is that the circuit, what we found here before, so from before, we said that the inductor goes to a short, the cap goes to an open, and what you're seeing here is that this Vs, that the voltage of the cap at infinity had to be the voltage of the 100 ohm resistor. And what we did here is that we went in and we did what? We said that this was going to be 100 divided by 100 plus 2 V source. So this is what? 1 divided by 1.02 V source. And you could see here is that we're getting the exact same value. So this checks out. And so therefore, our simple check is saying that it looks like it's good. Okay, so that is the direct method here. Okay, that is the direct method. So now what we're going to do here is that we got to go in, is we got to do the same thing with the operator method. Okay, the same thing with the operator method or Kramer's method. So what we'll do here is that I want to go in and make some new definitions. Okay, and what we'll do here is that it goes something like this. So now we're looking at method 2. This is Kramer's operator method. This should be your choice. Okay, this is super important to master this technique. Okay, you got to master this technique. Super, super important. So here we go, right? This should be your choice of method. So here we go. So what we're going to do here is that we're going to define operators. They're nothing like Laplace transforms. This is super, super simple operators. And what we're going to do here is that we're going to define simple operators and convert differentials and integrals into algebra equation, into algebra or algebraic expressions. So here I go. So I'm going to define the time derivative, and I'm going to use s hat. And then the integral of dt is then going to be defined as the inverse of this guy, which is of course equal to 1 over this. These are our operators. And so what it does here is it allows us to define simple equations in terms of algebra. So now we can rewrite the capacitor / inductor equations as follows here. We could come in here and we could do the following thing here. So check this out. So if I have the capacitor equation, I write this. So, and if I take the derivative of this guy, it's then going to be this guy here. So if I convert these guys, what do I see here? When I convert these guys into these operator equations, it really is IC equal to C S hat operating on this. Or I can write VS as 1 over C of S hat inverse IC. So these are my capacitor equations in this form here. Now, if I look at for the inductor here, I have VL is then L di dt, or I could take the integral of this and I get this here. So if I convert these guys into operator equations, what am I seeing here? Well, then this equation is then going to read VL is going to be L S hat IL, or IL is going to be 1 over L S hat inverse times VL. And what you're seeing here is that this doesn't look like it's a big deal, but it's a game changer. Okay? It is a game changer without any doubt here. And the reason why it's such a game changer is that we then can write a matrix equation for these operators. And it becomes powerful. And so we won't have time, but let me just sort of like paste it in here really quick so you could see where I'm headed. And what you're going to see here is that there's a lot of the process of method 1. We still define variables x1 and x2 just like we did before. We still have to use Kirchhoff's laws to get two equations with 4 unknowns. The big difference here is what happens in step 3 and 4. So now we have to convert our differential equations, our 2 first order equations, into algebraic equations in S hat. And once I do that, since I've turned them into algebra equations, I then use Kramer's method of solving a 2x2 matrix. And in that process, man, there's some stuff that comes out that is really, really powerful. And then once we solve that matrix equation, we could turn it into a differential equation if we want. And then, of course, we do the final step to check to see whether it's good or not. So the big difference is in step 3 and 4. Really, 4 is the one. Okay, I'm going to stop here. Thanks for showing up. I'll see you guys later. Good luck on the quiz.